In this lecture, I would like to extend the notion of PDF to the case of multiple random variables. So I want to talk about multiple random variables simultaneously. So we want to talk now about two random variables in the beginning that are continuous. So let me call these two random variables as x and y. These two are continuous random variables and they are jointly continuous. Continuous. And let's see what this means. The definition is similar to the definition we had for a single random variable. Okay, so the joint PDF is denoted by f sub x comma y and two parameters x and y. This is joint PDF. Okay, so the definition is similar to what we had for a single random variable. Okay, so in this formula I have taken two variables x and y. So this is a definition of your representation of your continuous random variable, and two random variables are said to be jointly continuous if we can calculate probabilities by integrating a certain function, and that we call the joint density function. So this is joint density function over the set of interest. So we have two-dimensional plane. Since we have two random variables, we have the two-dimensional plane. Let me call this is x and this is y. Okay, and this is x plane, xy plane, and there is a certain event we define, and that event let me denote by capital S. Okay, that we are interested in, or I can use some other notation. Let me say event E instead of S, event E that we are interested in. So we want to calculate the probability. So how do we do that? We are given this function fxy of x comma y is given. Okay, the joint density. So it is function of the two arguments. I have two arguments, x and y, two arguments. So think of that function as being some kind of surface that sits on top of the surface. Okay, on top of this two-dimensional surface. This is the two-dimensional surface. Surface. So let us think that this fxy of x comma y sits on top of this two-dimensional plane or two-dimensional surface. The probability of falling inside the set E, we calculate it by looking at the volume under the surface. Okay, that volume that sits on top of E. So the surface underneath it has a certain total volume. So what should that total volume be? Well, we think of these volumes as probabilities. Therefore, these volumes we think of as probabilities. So we have the two-dimensional surface. On top of the two-dimensional surface, our density function is sitting. This function is sitting on top of the two-dimensional surface. Okay, so therefore we think of these volumes as probabilities, and we know that the total probability should be equal to 1. That means what? You integrate x from minus infinity to plus infinity, and integrate y from minus infinity to plus infinity over the density function fxy of x comma y. By total probability theorem, it should be equal to 1. So that's the one property that we want our density function to have. So when you integrate over the entire space, what do you mean by from minus infinity to plus infinity? That means we are integrating over the entire surface or entire plane. And that should be equal to 1. So this one is the volume. This integration will give you the volume under your surface, that should be equal to 1. Of course, since we are talking about probabilities, the joint density should be non-negative function. Therefore, the joint density function f sub x, capital X comma y This should be non-negative function. Non-negative function. So think of the situation as having 1 kilogram of probability that is spread all over your space. Okay, so that is spread all over your space x and y plane. And the height of this joint density function basically tells you how much probability tends to be accumulated in certain regions of space as opposed to other parts of the space. In some space, the probability will be more likely to occur. More likely to occur. And some space, it is less likely to occur. Less likely to occur. Okay, therefore we can think that the density will tell you how much the probability is accumulated in a certain region of space as opposed to other parts of the space. Therefore, whenever the density or wherever the density is big, that means there the area of the two-dimensional plane, that is the values are going to occur more likely. And wherever the density is smaller, there the likelihoodness of the value that is going to occur is very less. Therefore, where the density is small, that means that those xy's are less likely to occur. And we have already seen one example in one-dimensional random variable. That very famous and elementary example is uniform random variable, where the density is from a to b and b minus a. This is fx of x. The same kind of example that we can develop in two-dimensional random variable also. So you consider a square in the two-dimensional plane. This is x and this is y, and you consider a square, unit square. Unit square. And this is special case of a density function that was constant. So it is a constant across all over this unit square. That means what? Some parts of the space may not be more likely than others. Okay, in other models, some parts of the space may be more likely than others. But here, all places in the unit square were roughly equally likely as any other places. Therefore, we describe the relative likelihoods using the density function. Now, somebody gives us a density function, and how do you calculate the probabilities? Okay, how do you calculate the probability? Therefore, let me take the diagram. So I have the xy plane, and I want to find out the probability from the density function. I have the density function in this space. Let me define the density function. No, this is a event, and I have the density function here. Density function on x and y, xy plane. Okay, now we need to find out the probability of this density function in the two-dimensional plane. Now for an intuitive interpretation, again it is good to think about small events. Let us take a small event. So in that situation, again I will take this is my little x small, and this is x plus delta. Okay, so this is x-axis and this one is y-axis. Okay, so I am taking a particular x here, and then x plus delta x in this point here. Okay, so this is a small interval, right? And let me take maybe I'll draw this figure. So it is running all over y. Okay, and let me take another small interval here. Okay, so this point is little y, and this one is y plus delta. Therefore extend here. So I may get a small area. This area let me call a rectangle. So instead of calling a rectangle, because here the width is delta and here also the width is delta, let me call a square. Okay, so what is this event? This one, what is this event? Well, this is an event that will fall inside this little rectangle or square. So using this rule for calculating probabilities, what is the probability of that rectangle going to be? Well, it should be the integral of the density over this rectangle. You take the density function fx comma y of x comma y and integrate. So x ranges from x to x plus delta and y ranges from y plus delta dx and dy. So now if the rectangle is very small, the joint density is not going to change very much in that neighborhood. Therefore we can say this is constant in that neighborhood. Since the interval is very less, very small, so the joint density is going to change very much, not going to change very much in that neighborhood. So we can treat it as a constant. So this fxy of x comma y can be treated as constant. So the volume is going to be, since this is a volume, right? So the volume is going to be height times the area of the base. What is the height? This is F here, fxy of x comma y times delta square. And what is the probability of this event, this particular this event? How do you write mathematically this one? This event is probability of your x lies between random variable x lies between small x, capital X less than or equal to x plus delta, and the random variable y lies between small little y to y plus delta, right? Therefore the left hand side is going to be probability of little x less than or equal to random variable x plus delta, comma little y less than or equal to capital Y less than or equal to y plus delta. Therefore it specifies for you probabilities of little squares, and it allows you to think of the joint density function as a probability per unit area. Why is it called a probability per unit area? Say this is joint density function, right? Joint probability density function. You take this delta to the left hand side. If you take it to the left hand side, then you will get like this: little x small less than or equal to x plus delta, comma y capital Y less than or equal to y plus delta, whole divided by delta square is equal to fx comma y of x comma y. See, this is a joint density function. What is a joint density function? Which is equal to this probability by delta square. So in the numerator we have probability, the denominator we have area, right? Therefore you can interpret the joint density function as probability per unit area. Probability per unit area. So this is your joint PDF or joint density function. So these are the units of density. Its probability per unit area in the neighborhood of a certain point. Now you can ask a question: what do we do with this density function once we have it on our hands? Well, we can use it to calculate the expected value. So the next topic is expected value. Expected value of fxy of fxy. Okay, suppose that you have a function of two random variables described by this joint density function fxy of x comma y. Okay, and you can find perhaps the distribution of this random variable. You take another random variable function of x and y. So let me call the random variable z, which is the function of the random variable g of x comma y. It's a function of the random variable x comma y. And how do you find out the expected value of z? Expected value of the random variable z. Either you can find the probability density function of z. The first method is you can calculate the probability density function of z and then calculate E of z, expected value of z. Or no need to find out the probability density function of z. You can directly calculate the expected value of z from the probability density function of x and y itself. So no need to calculate the distribution function of z, that is distribution function of g of x comma y. Okay, so you use the basic definition of the expectation and you can calculate the expectation directly using the distribution of the original random variables. Therefore, the expectation is given by g of x comma y, which is equal to double integral g of small x comma y times the original density function fxy of x comma y times dx dy, and the limit is from minus infinity to plus infinity. So this is the formula, okay, that again identical to the formula that we had for the discrete case. Okay, in the discrete case we had a double sum. So instead of double integration, see here we have double integration. So instead of double integration, we had double sum, and instead of the density function, we had a joint PMFs. So Pxy of x comma y, and here the same function g of x comma y. Okay, so the intuition behind this formula, this continuous formula, let me call this formula 1. So the intuition from this formula is the same that one had for the discrete case. So it is just that mechanics are different. Okay, here we used the probability density functions and a double integral, and here we used summation, double summation, and probability mass functions. So therefore we are moving from joint density of the two random variables to the joint density of probability mass functions. Okay, and so we had a formula for the discrete case, and now let us see how we can interpret the continuous case than the discrete case. So the interpretation is little subtle, that we will see how we can interpret. So let's see how things are going to work out in the continuous case than in the discrete case. In the continuous case, we have here our two random variables x and y, right, and we have a density for them. The density we denoted by fxy of x comma y, and let's say that we want to calculate the probability that x falls inside the little interval. Let me say this is little x and this is x plus delta. So how do you find the probability which falls on this little interval? So look at this figure. Your x lies between x to x plus delta, capital X plus delta. What about y? It lies between minus infinity to plus infinity. Now how do you describe this event mathematically? Probability of your x lies between little x to x plus delta. This is my probability. Alright. Now how do you find out this event, or how do you find out this probability? Then let's see how we can do that. So we have a density for them, and let's say that we want to calculate this probability that x falls inside this interval. So we are looking at the probability that our random variable x falls inside the interval from little x to x plus delta. Now by the properties that we already have for interpreting the density function of a single random variable, see, this is the probability of a single random variable. We are not considering y here, okay, because you are considering very small interval of x here. So the probability of little interval is approximately the density of that single random variable times delta, that we already know, that we already discussed in the previous lectures. Okay, therefore the probability of x, capital X, less than or equal to x plus delta, this is approximately equal to your density function, f single random variable density function fx times of x times delta. So this we already proved when we discussed a single random variable. Okay, and there is another name for this, and this is called a marginal density function. So later on we will see how we can get marginal density function from the joint density function. And now we want to find the formula for this marginal density function in terms of joint density function. Our problem is we need to know how to move from joint density function to marginal density function. We have joint density function to marginal density function. That we will see how we can move. Okay, so now this is the probability. Okay, P of x less than or equal to capital X less than or equal to x plus delta is the probability that x falls inside this interval x to x plus delta. In terms of the two-dimensional plane, this is the probability that xy falls inside this strip. This is a strip, right? So to find the probability, we need to calculate the probability that xy falls in this shaded area. Okay, so which is going to be double integral of your density function fxy of x comma y dx and dy, and x varies from little interval little x to little x plus delta, and y, look at the figure here, y ranges from minus infinity to, sorry, this is not y, this is infinity, I'm sorry, minus infinity to plus infinity. Okay, so now you do this integral. So y goes from minus infinity to plus infinity, and the dummy variable x goes from little x to x plus delta. So integrate over this strip. So what we do is, for any y, we integrate in this dimension, okay, from x to x plus delta. So this one is the x integral. Okay, so and then we integrate over the y dimension. Once you do, first you do the x integral and then do the integral in the y dimension. So now what is this inner integral is going to be? Inner integral. We said the inner integral is going to be constant over the interval from x to x plus delta, because we said the density times the delta. Therefore the inner integral is going to be minus infinity to plus infinity fxy of xy comma y times delta and then dy. And since delta is constant, you can take out delta outside. Delta times integral minus infinity plus infinity fxy times of x comma y times dy. What is the left hand side? Your left hand side is going to be P of x less than or equal to x less than or equal to x plus delta. Okay, so this is the left hand side, and this one we already proved that this is equal to delta times fx of x, which is equal to delta times integral fxy of x comma y times dy, and this delta will get cancelled, and you will end up with fx of x, which is integral from minus infinity to plus infinity fxy of x comma y times dy. Okay, so now this is what we are getting here. Now there is no surprise at this point. It is exactly the same formula, same as the formula that we had for discrete random variables. In the discrete random variables also we had the same formula. Instead of that, this integration is replaced by summation over y, and instead of the density function we had the joint probability mass functions. Okay, and this is equal to probability mass function of px of x. Okay, so at this point let me finish this, and now we will finish this joint density functions, and now we will do a small example on this. Now the problem is given, and I have taken this problem from a textbook titled Introduction to Probability Theory by John Tsoukalis. It is available in the website, and you can go through this problem. The problem is, we are told that the joint PDF of the random variable x and y is constant, and that constant is c. On the set S shown in the figure, the figure is, this is 3.12 in the textbook. Okay, you can go through. And is 0 outside. So here it is 0. In this outside the interval it is 0 everywhere. Say this is this is x axis and this is y axis. In the xy plane, you have there is a PDF, and the PDF is constant everywhere. Okay, it's a constant means it is equally likely all the points, and it is 0 outside the this PDF, outside the set S. We wish to determine the value of C and the marginal PDFs of X and Y. So we need to find out what is the value of C and the marginal PDFs of X and Y. Now when you want to find the constant C, so how do you do that? So let me write down the joint density function denoted by fxy of x comma y, and we know that the total probability should be equal to 1, not should be equal to 1, it must be equal to 1. Therefore when you integrate the joint density function fxy of x comma y dx times dy, which is equal to 1. So this is essentially the area. The area should be equal to 1. Now you can find out the area straight away from this. It's a simple structure, so you can find out the area straight away. And if you take this, maybe I'll choose different colors. If you choose this area, this is the width is 1 and this width is 1, so therefore area equal to 1 in this one. You take this also again a square, and this area is 1. You take this area, this also 1, and take this area again, this also 1. Therefore the total area equal to 4. Therefore this should be equal to 1. So in the left hand side it is constant times fxy of x comma y dx dy. This should be equal to 1. Therefore 4 times c equal to 1. The c equal to 1 by 4. 1 by 4. Therefore your fxy of x comma y is equal to 1 by c, which is 1 by 4. This is my joint PDF, probability density function. That's it. Now we need to find out what is the marginal density. As I said, fx of x comma is called a marginal density or marginal probability density function of the joint density function fxy of x comma y. This is marginal probability density. Similarly, we need to find out fy of y. So let me do fx of x in this, and fy of you can do on your own. It's similar. By the same token, you can work on it. Now, how do you find out fxy of x comma y? Maybe I'll take this figure, copy, I'll paste somewhere else. Paste. Now let me find out fx of x. So the fx of x is given as follows. Let me put a figure. Let me change the color. Fx of x. What is fx of x? You integrate from minus infinity to plus infinity the joint density function fxy of x comma y dy. Okay. So when you take this fx of x, that means what? You are taking certain interval on the x-axis where x is constant. Okay, x is not changing much. Therefore, what you do is you take a small interval. In this interval, x is not changing. Okay, so you take interval by basis interval. Therefore, if you take, so in this interval from 1 to 2, where x lies between, let's say, 1 less than or equal to x less than or equal to, let me take, this is my small interval. Though it is small interval, let me take it is small interval. Small interval, okay, where y is constant. You see the y is constant in this interval, the y is constant, it is not changing. So therefore you take this rectangle as like this, it is constant, the y is not changing, it is constant. Okay, therefore the constant value is going to be, let me write down this one, your y lies between 1 to 4. Okay, therefore the range is 1 to 4. Your fx of x comma y times dy is 1 by 4 times dy. So 1 by 4, the limit is 1 to 4, it is 3. So this is 3 by 4. Therefore, your fx of x, which is equal to 3 by 4 in the interval, let's say 1 less than or equal to x less than or equal to 4. This is one density, one part of the density, marginal density function. And what about the other part? And take this interval when x lies between 2 to 3, 2 less than or equal to x less than or equal to 3. So in this part, what happens? Your y lies between 2 to 3. Therefore, your fx of x equal to integral of the limit is 2 to 3 fxy of times dy. This is anyway constant 1 by 4. You substitute there, integral of 2 to 3 1 by 4 dy, and this is anyway 1 by 4 times y. The limit is 2 to 3, which is 1 by 4. Therefore, fx of x equal to 1 by 4, 1 less than or equal to, sorry, this is it 4? No, this is not 4, I am sorry. This is 1 to 2. This is 1 to 2, and this is 2 to 3. So you can look at here, this is 2 to 3 and this is 1 to 2. If you draw the figure, then the figure would look like this. Okay, so the figure will be as follows. From this is 0, 1, 2 and 3. 1 to 3, the height is this much, 3 by 4, and 2 to 4, the height is 1 by 4. Now again I need to verify whether this is a legitimate PDF. This is this is fx of x, and is fx of x a legitimate PDF? That is a question we need to answer. When we say a legitimate PDF, two conditions it must satisfy. What are those conditions? The total area should be equal to 1. What is the total area in this one? This is equal to 3 by 4 times 1, which is equal to 3 by 4. What is the area in this small rectangle? This is equal to width times height. Width is 1 and height is 1 by 4. So total area is 1 by 4. So 1 by 4 plus 3 by 4, which is 1. Therefore, this is a legitimate PDF. And fx of x is always non-negative. Therefore, this is a legitimate PDF. By similar procedure, you can calculate fy of y also. That I leave it as an exercise, or you can look at this problem in the textbook. Okay. So at this point, I will stop this lecture. In the next lecture, we will continue the notion of independence of multiple random variables. We will start with 2 random variables, and then the same thing we can extend to n number of random variables. Okay. Thank you very much.